Hello everyone. Today we are in the week 10 of the live interaction session, and in this session we'll be discussing the contents of week 11. So the week 11 lectures are on a new module, which is the hydrological statistics module. So the hydrologic statistics helps us to estimate some of the flood magnitude, extreme flood events by using certain probability distributions. So we'll be seeing in this lecture some basic concepts related to the probability, numericals related to the conditional probability and total probability, and later we'll be seeing how to estimate flood magnitude for a certain return period when normal distribution is given, and later on we'll be seeing Gumbel distribution, which is the estimation of the extreme flood events. Uh, So let's move on to the problems for today's session. So this is the question number 1. So the probability of rainfall occurring on the first day of a month is given as 0.3. And the probability that rainfall will occur on the first 2 days of the month is 0.12. Now we need to find the probability of occurrence of rainfall on the second day, given that the rainfall occurred on the first day of the month. So here what we need to notice, here we need to find the probability on the second day, given that the rainfall has occurred on the first day, which means we need to use the conditional probability in this question. So let us say the probability of rainfall which is occurring on the first day as a probability of A, and on second day as P of B. So rainfall occurring on both days will be given as probability of A intersection B. Now we need to find the probability of rainfall, occurrence of rainfall on the second day. So the probability of rainfall occurring on a second day is probability of B, given that, so I am putting a conditional probability here, that the rainfall has occurred on the first day. So from the laws of probability, we know probability of B given A can be written as probability of A intersection B divided by probability of B. So this can be written as 0.12 divided by 0.3. This is given in the question. So the probability of occurrence of rainfall on the second day, given that rainfall occurred on the first day, is 0.4. So let's move on to the second question. The question is, an embankment may fail either due to overtopping or due to seepage or simultaneous occurrence of both. The probability of failure due to overtopping is given as 0.4, and due to seepage it is given as 0.15, and the simultaneous occurrence of both overtopping and seepage is given as 0.10. Now we need to find what is the probability of failure of the embankment. So for this, if we see, we can make use of Venn diagram for this case. So this is the total sample space, and let the overtopping be named as A, and seepage failure due to seepage be named as B, and this is the intersection of both overtopping and seepage. Now we need to find what is the total probability of failure. So we need to compute A union B in this case. So from this we can write probability of A union B can be written as probability of A plus probability of B minus probability of A intersection B. So here A refers to failure due to overtopping, B refers to failure due to seepage, then A intersection is a simultaneous occurrence of both. So we can find, it's a straightforward question, we can find what is the probability of failure. So which is 0.4 plus 0.15 minus 0.10. Which is 0.45. Okay, let's move on to question number 3. So the question number 3 is, the flood damages at a location are caused mainly due to poor management of mitigation measures, which are either structural or non-structural measures. So the Flood Management Authority analyzes the various issues involved and found that the possibility of improving the structural and non-structural measures are 70% and 55% respectively. If only one of these two measures are implemented, the probability of preventing the flood damages is 80%. Assuming that the flood damages are caused by poor management of structural and non-structural measures are independent, then find the following. What is the probability of preventing the flood damages? And if the flood damages are not prevented, then what is the probability that it is entirely caused by failure due to mismanagement of the non-structural measures? So here they have already given probability of preventing the flood damages, but we need to find out what is the total probability of total probability of preventing the flood damages if either of the measures are improved. So for the first part of the question, we will be using the law of total probability. So here we need to find total probability of preventing the flood damages. And we have two options. We can improve structural measure, or we can improve non-structural measure. And there is also one more possible case which can happen, which is the improvement of both. That is complete prevention of flood damages. That is also one of the component in the total probability. The last case is the complete prevention. So in question, if we improve either one of these two structural measure or non-structural measure, probability of prevention of flood is given as 0.8, and for complete prevention it will be 1. So if I name it as case A, B and C, this is for A and B, and this is for C. So now we need to find out total probability of total prevention. So this can be written as probability of structural measure So in the first case, we are improving the structural measure, which means we are not improving the non-structural measure. So since we are not improving, it is a complement to the probability. So I am giving a complement to that. Into probability of prevention, which is nothing but a 0.8. So this is the first part. And in the second case, we are not going to improve the structural measure, but we will improve the non-structural measure. Into probability of prevention. So these are the two cases, A and B, and for the last case we will improve both. And here the probability is complete prevention. So we can calculate the total probability of prevention is. So if we improve structural, probability of improving the structural measure is 0.7, and probability of not improving the non-structural measure is 1 minus 0.55, and probability of prevention is 0.8. So this is the first part. And for the second part, it is 1 minus 0.7. We are not improving the structural measure, but we are improving the non-structural measure multiplied by 0.8. And the third part is we are improving both the measures. into complete prevention is probability is 1. So if you calculate, this will be 0.769. So this is the answer for the first part. And in the second part, damages are not prevented. What is the probability that it is entirely caused? So you should note this word entirely, due to the mismanagement of only the non-structural measures. So it is like we need to use the Bayes theorem in this case, because damages are not prevented. So what is the probability that it is coming from the non-structural measures? So here we need to use the Bayes theorem. So since only entirely non-structural measures is to be taken, we will be disregarding the poor management of the structural measures. So we will not be taking any component in the numerator which corresponds to the poor management of structural measures. That is the only difference in this question. So we can find out the probability. Probability of improving the structural measures into, we are not going to improve the non-structural measures. So since we are not going to improve, I am going to give a complement. And here we need to find out what is the probability of failure. So flood is not prevented. So here we'll be writing the complement of prevention. This whole thing has to be divided by the total probability, the complement of the total probability, since we are going to find out what is the probability of failure. So complement of probability of total prevention. So probability of improving structural measure is 0.7. Not improving structural measure, not improving the non-structural measure is 1 minus 0.55 into 1 minus 0.8 divided by 1 minus total probability, that is 0.769. So the probability due to the mismanagement of non-structural measure is 0.273. So this is your answer for the second part. So let's move on to question number 4. This is related to the probability distribution. Here we are going to see the discrete probability distribution. So the question is, the number of rainy days in the last week of December at a location is found to follow a certain distribution whose probability mass function is given by P of x is equal to C, which is some constant, when x takes the value 0, and e power minus 1 divided by 2x when x takes the value from 1 to 7, and it is 0 elsewhere. Now we need to evaluate the value of C such that this P of x is a valid probability mass function, and we also need to find out the probability that the last week of December has more than 2 rainy days. So this is a classical problem for a discrete probability distribution. So for the given distribution to be a valid PMF, it has to satisfy this condition. Summation of phi is equal to 1 to n. P of xi should be equal to 1. So the summation of all the probabilities should be equal to 1. And here x can vary from 0 until 7. So when x is equal to 0, the value of P of x is equal to C. So I am writing C when x is equal to 0. From 1 to 7, it is taking the value of e power minus 1 divided by 2x. Now we need to sum up everything. So I am adding a summation. I is equal to, here it takes from 1 to 7 xi plus any value that is more than 7, your PMF takes the value 0. It is outside the range. So this should be equal to 1. Now we can substitute the value for x. So that will be C plus, it will be like 1 divided by, I am bringing the e to the denominator since it is e power minus 1, plus 1 divided by 2 into e into 2, so on until 1 divided by 2 into e into 7 should be equal to 1. So if we simplify this, so e takes the value of e power 1. So you can compute this in the calculator. So your C will be equal to 0.5231. So if C takes the value of 0.5231, then the given PMF is valid. So this is the first part of the question. In the second part, we need to find out what is the probability that there are more than 2 rainy days. So I am writing probability of x greater than 2 in the last week of December. So this can be written as 1 minus probability of x less than or equal to 2. So we can find out 1 minus probability of x equal to 0 plus probability of x equal to 1 plus probability of x is equal to 2. So if we subtract from the total probability these three probabilities, then we can get the probability of x greater than 2. So when x takes the value 0, it is simply c. So it will be 0.5231. And for probability of x equal to 1, 1 divided by 2 into e into 1 plus 1 divided by 2 into e into 2. So upon simplifying this, we can get a probability of x greater than 2. So it is only 0.201. So which is 20.1 percentage. So we'll move on to question number 5. The question number 5 is, a 30-day month contains 10 rainy days, which can also be called as wet days, and 20 non-rainy days, which are called as dry days. So given that the probability of 2 consecutive days being wet is 0.125, what is the probability that a wet day is followed by a dry day? So this is again similar to the first question, which is using the conditional probability. So here wet day is followed by a dry day. This is the statement which you need to understand. So let's move on to the solution. So I'm calling the event A as first day being wet. And event B as second day being wet. So event A complement will be first day being dry, and event B complement will be second day being dry. So let us find out the probability of A. Probability of A is what is the first day being wet. So there are total of 10 rainy days, and the total number of days is 3. So that is 1 by 3. So probability of B is also similar to that, 1 by 3. And the probability of A complement is 1 minus probability of A, which will be equal to 2 by 3. And probability of B complement is 1 minus probability of B, that is also 2 by 3. Now understand the statement. Wet day is followed by a dry day. So your first day is dry day and the second day is wet day. Now we need to find probability of wet day that is followed by a dry day. So your first day is wet day and your second day is dry day. So wet day is followed by a dry day. So we can find out probability of B complement given A. This can also be written as 1 minus probability of B given A. So if we simplify further, 1 minus probability of B intersection A divided by probability of A. So probability of B complement given A is probability of B intersection A is rainfall occurring consecutively on both the days, that is given as 0.125, which is nothing but 1 by 8 divided by probability of A we found as 1 by 3. So this will be 1 minus 3 by 8. So probability of B complement given A is 5 by 8. So similarly, you can also find what is the probability of dry day that is followed by a wet day. You can try this. Probability of dry day followed by wet day. That is probability of B given A complement. So let us move on to question number 6. This is related to the estimation of the flood magnitude and return period when the annual maxima series for any given stream follows a certain distribution. So the question is, the mean and the standard deviation for annual flood peak series was found to be 5651 meter cube per second, and the standard deviation was 1066 meter cube per second. The annual maximum series was found to follow a normal distribution. Now we need to determine what is the probability of a flood being between 6000 and 7000 meter cube per second during any year. And the probability of exceedance of flood of magnitude 7500 meter cube per second, and the flood magnitude of a return period of 100 years. Now let's see how to solve this question. So for the first question, we are asked to estimate what is the probability of flood being between 6000 to 7000. The next step is to find out the standard normal variate. So here we are applying a transformation, that is x minus mu divided by sigma. So we'll find corresponding to Z1 and Z2. Z1 corresponds to 6000. So 6000 minus mean is 5651. Standard deviation is 1066. This gives us a Z value of 0.327. And we'll compute the Z2 also. 7000 minus 5651 divided by 1066, that gives us 1.265. So now we are going to make use of the normal distribution to determine the value of the probability. So let's say that this corresponds to 6000 and this corresponds to 7000. and we are going to find out what is the area under this particular curve. So we cannot make use of this directly. So we have applied a transformation and we have converted the x into the standard normal variate, which corresponds to z1 is equal to z1 is equal to 0.327 and z2 is equal to 1.265. Now we need to estimate the area under this curve. So from the standard normal table, we can find out this values. So which means we'll be finding out the area under this curve for 0.327 and for 1.265 we'll be finding out this entire area. The difference of these two will give the, so if you subtract these two, you will get the area under this curve. So I have already calculated what is the area under the curve. So for Z1, area under the curve is nothing but the cumulative probability. So Z1 is 6000. So capital F of 6000, that is 0.6285. For Z2, it is 7000, that is 0.8970. So your probability of X lying between 6000 and 7000 can be written like this now. Probability that Z lies between 0.327 and 1.265. This can be written as f of 7000 minus f of 6000, that is equal to 0.8970 minus 0.6285. So this will be equal to 0.268. The probability is only 26.8%. So this is the first part of the question. For the second part, we need to estimate what is the probability of X greater than 7500. So this can be written as 1 minus probability of X less than or equal to 7500. Now we need to find Z3 which corresponds to x of 7500. This is 5651 divided by 10, similar to the previous. So the z value is 1.734. For 1.734, the probability from the standard normal table is found as 0.9585. Now we can find out the probability of x greater than 7500. This can be written as probability of z less than or equal to 1.734. That is nothing but 1 minus f of 7500 0.0415, that is only 4%. The part C of the question, we need to find out what is the x value corresponding to a 100-year return period. So for that, the return period is given as 100 years. So when the return period is given, we can find out what is the probability. So probability is equal to the inverse of the return period, which is 1 by 100, and it is 0.01. So we need to find what is the probability of x greater than x 100. That is nothing but 1 minus probability of x less than or equal to x 100. So whatever we found was 1 minus probability of x less than 100, 1 minus 0.01, that is 0.99. So this is the probability. So in the standard normal table, we need to look at where the probability is 0.99, and we need to find out the corresponding z value. For a z value of 2.33, we will get the probability of 0.99. So we can interpolate between the two given ranges, and then we can find out what is the z value. Now once we get the z, we have this transformation function. Z is equal to x100 minus the mean, that is 5651, divided by standard deviation. So z is known. We can find out what is x100 from this. So x100 is equal to 5651 plus 2.33 into 1066. So x100 is 8134.78 meter cube per second. So this is the magnitude of a 100-year return period event. So next question is related to the continuous probability distribution. Here the annual minimum flow in a river is known to vary between 4 meter cube per second and 10 meter cube per second, and they have a probability distribution of the form which follows a certain density function which is given by f of x is equal to alpha by x squared. So here x refers to the annual minimum flows. Now we need to find what is the value of alpha such that the given function is a valid probability density function, and the return period for a flow of 7 meter cube per second. And lastly, we need to find what is the mean and the standard deviation of the annual minimum flows. So first part is we need to determine the alpha. Similar to the discrete problem which we saw earlier, for any function to be a valid probability density function, it should follow a certain condition. So for a valid probability density function, integral of minus infinity to plus infinity f of x dx should be equal to 1. But here the limits vary between 4 and 10. So we can find out the value of alpha by integrating between 4 and 10. Function is alpha by x square dx. This should be equal to 1. So if you integrate this, you will get alpha as 6.67. So this is the first part of the question. Second part is we need to find out what is the return period for a flow of 7 meter cube per second. So we have the probability density function. We can just substitute probability x equal to 7. So that is alpha by x square, 6.67 divided by 7 square. We can get probability of x equal to 7 as 0.136. So once we get the probability, we can get the return period as 1 divided by p, 1 divided by 0.136, that is equal to 7.35 years. And the last part of the question is to determine the mean and the standard deviation. So the mean can be determined as integral minus infinity to infinity x f of x dx, and we can find out the variance as integral minus infinity to infinity x minus mu the whole square f of x dx, and standard deviation is square root of variance. So this is what we are going to do. So first we'll be doing we'll find out the mean. So we'll integrate between 4 to 10 again, x into f of x dx, alpha by x square into dx, which will give us integral 4 to 10, alpha is 6.67 divided by x into dx. So mu is equal to, so 1 by integral of 1 by x is natural logarithm. So it will be ln of upper limit minus ln of lower limit. So we can find the mean as 6.11. Next we need to find out the variance. So again we are going to integrate from minus infinity to, we are going to integrate from minus 4 to plus 4, minus, sorry, 10 to 4 to 10, and x minus mu the whole square, so x minus 6.11 the whole square into alpha by x square dx. So if we simplify this, we'll get the variance as 2.6863, and the standard deviation square root of 2.6863, that is 1.6389. So when a continuous probability distribution density function is given, you can find out the mean and the standard deviation by using this method. So before moving to the next question, we can see something about Gumbel's distribution for extremes. So we'll be seeing about Gumbel's distribution for maxima. There is also Gumbel distribution for minima. So the Gumbel's distribution falls under the category of extreme value type 1 distribution, and the cumulative density function, which is nothing but the capital F, is given by double exponential of y minus beta divided by alpha. So this is a double exponential. Here y varies between minus infinity to plus infinity. Beta also varies between minus infinity to plus infinity, but alpha is always greater than 0. And alpha is the scale parameter, and beta is the location parameter. And the PDF, which is the probability density function, it is given by, which is nothing but df by dy it is given by 1 divided by alpha exponential of minus y minus beta by alpha minus again another exponential of y minus beta by alpha. And the mean of the distribution is given by v is equal to beta plus 0.5772 alpha, and the variance is given by variance of y, that is pi square alpha square divided by 6, and the skewness coefficient of this particular distribution is 1.1396, and it is positive. Now there is also one more thing which you need to know. This will be using to find out the value of different annual maximas, that is the inverse CDF. It is also called as the quantile function. That is nothing but y of f. It is given by beta minus alpha into ln of ln into f. So this is one way to represent, or you can write f in terms of the return period, which has been derived in class already. So y in terms of return period is given by beta minus alpha into ln of minus ln 1 minus 1 by t. So this expression may be similar to, which this was derived in the class, where t refers to return period, and there is also one more note. The quantile value for E of y that is mean annual flow. Has a return period of 2.33 years. So these are the things which you may need to remember to solve a question on Gumbel's distribution. So let's move on to question related to the Gumbel's distribution. So the first question is, flood frequency computation in the river Chambal was carried out using Gumbel's distribution. And it was found that for a return period of 50 years, the peak flood was 40,809, and for a return period of 100 years, it is 46,300. Now we need to estimate the flood magnitude in this river for a return period of 500 years by using the Gumbel's distribution. So we know that for Gumbel's distribution, so to estimate the flood, we write the general expression as x is equal to mean plus kt into sigma. So this is the general transformation equation that we use in the Gumbel's distribution. So here we are being provided with two information. One is x100, that is equal to, so this is sigma n minus 1. So mu plus k50 into sigma n minus 1. This is one condition. And for 50-year return period also we can write the same. K50 into sigma n minus 1. Now if we subtract in this, both the left hand side is known, but the right hand side is not known to us. So I'm naming equation 1 and 2. So I'm going to take a difference between two. Subtracting 1 and 2, we get x100 minus x50 will be equal to sigma n minus 1 is common, so I'm keeping it outside. K100 minus K50. So this is equation 3. And we also know that Kt is the frequency factor. And frequency factor for Gumbel's distribution is given by Yt minus Yn bar divided by Sn, where Yt is the reduced variate and Sn is the standard deviation for the sample that is considered. And Yn bar and Sn bar are constants, and it is available from standard tables. So for a given sample size, this Yn bar and Sn will change. And we saw the quantile function that we can write Yt as minus natural logarithm of, again a logarithm, t divided by t minus 1. So this is an expression which was derived in the video lecture for Yt. So we can write for Y50 and Y100. So minus ln of ln into, this is a 50-year return period. So this is 50 minus 1. And if we compute this, this is equal to 3.9019. Similarly, we can compute for Y100, 100 by 100 minus 1. So this is 4.600. So now we are going to substitute Y100 and Y50 in the Kt equation, and we are going to determine what is the value of Y100 minus Y50. So we can write like from the equation 3. So equation 3 is x100 minus x50. So we know the value for x100 and x50. So we can find out the value for sigma n minus 1 into k100 minus k50. That will be 46300 minus 40809. So sigma n minus 1 k100 minus k50 can be written as 5491. So now I am going to take y100 minus y50. This is from the equation 4 I am going to do. So let me write yt is equal to kt into Sn plus yn bar. So if I write y100 minus y50, it will be k100 minus k50 into Sn, and yn will get cancelled. And from this I can write k100 minus k50, we can substitute. So from equation 5, substitute k100 minus k50. So y100 minus y50 will be equal to k100 minus k50 will be 5491 into Sn divided by sigma n minus 1. Now we know the value for y100 also, y50 also. So we can find out what is sigma n minus 1 divided by Sn. So that will be equal to 5491 divided by y100 minus y50, that is 4.6 minus 3.9019. So sigma n minus 1 divided by Sn will be equal to 7864. So let me keep this as equation number 6. Now we can find what is y500, since we need to find out the magnitude of the event. So this is equal to 6.2136. Now if I do the similar process for y500 minus y100, we will get x500 minus x100 into Sn divided by sigma n minus 1. So this 5491 is nothing but the difference between x100 minus x50. So I am rewriting the same equation between y500 and y100. So y500 minus y100, we can find out what is the value. 6.2136 minus 4.6, that should be equal to x500 minus x100 value we know, which is 46,300, and sigma n minus 1 by Sn, we found it as 7864. Here it is the reciprocal of that, so it will be 1 divided by 7864. So in this only unknown is x500. We can solve for it. and x500 will be equal to 58,988 meter cube per second. So this is the way to solve. So here you need to remember uh, why we are getting this value sigma n minus 1 by Sn, and how we are writing this expression. So these are the key places which you need to know. So last question for the today's session is Engineering Services 1996 mains exam question. In this, for data of maximum recorded flood of river, the mean and the standard deviation are given. Using Gumbel's distribution, we need to estimate the return period for a flood of 9,550 meter cube per second, and here we can assume the infinite sample size. So xt is 9,550, and we need to find out what is the value of t, and mean is given as 4,200 meter cube per second, and the standard deviation is given as 1,705 meter cube per second. So we know we can write xt as x bar plus kt into s, and here kt is equal to yt minus yn bar divided by Sn, but for an infinite sample size we can assume yn bar as 0.577 and Sn as 1.2825. So this we can assume when the infinite sample is given. Now we can substitute in the above equation and find out what is the value of yt. So 9550 is xt, which is equal to mean is 4,200 plus k is given as yt minus yn bar divided by Sn into standard deviation, which is 1705. Now from this we can estimate yt as 4.6013. So we have now estimated what is the reduced variate. Now we need to find out what is the return period, which is given by t by t minus 1. This is the value for, this is the formula for yt. Now we can find out what is value of t, which is given by minus ln of n t divided by t minus 1. So if we take the first natural logarithm to the other side, we will get e power minus 4.6013, that is equal to ln of t divided by t minus 1. So this is approximately 0.01. We can find out. And again, if we take the ln to the other side, this will be e power 0.01. So from this we can find out t is equal to 1.0101 to t minus 1. From this we can estimate T to be approximately 100.01 years. So the given flood of 9,550 meter cube per second has a return period of 9,100 years. So that's it for today's session. I hope it is useful to you. Thank you.